Last time, we talked about how delta G and K are inextricably related. That if you have a very, very big K value, that means you have a monster product value, right? So products of reactants. If they're a huge K value, that means the reaction is going to proceed mostly to the products. And then we can plug them into our conversion equations and find that that's going to return a negative delta G. So far, so good. The opposite is also true. If you have a tiny K value, that is less than 1, that means you're reactant favored, and you're going to return a positive delta G. Now, this is the reason we do that before electrochem. In electrochemistry, some metals are more active than other metals. In other words, some metals would rather be in ions or solutions than actual metals. We learned last year and a bit this year that the oxidation state of an element is 0. Oxidation of ion is positive or negative. When we deal with electrochemistry, we almost always deal with metals that want to be positive ions. So we have extremely active metals like lithium and sodium that would rather be positive 1 ions. And extremely low activity metals like gold, silver, and platinum that would like to be 0, would like to be metals. These metals we can actually dig up out of the ground and find like, hey, look, I found a chunk of gold. I found a chunk of platinum. I found a chunk of silver. The reason we can find chunks of those metals is because they have a very, very low activity. You will never find a chunk of lithium. Lithium will be found as a compound with lithium plus 1. So far, so good? Okay, so review our oxidation. Oxidation state is 0 when the protons equals the electrons or any free element. A positive oxidation, you have more protons than electrons. A negative oxidation, more electrons than protons. And if you have a situation where you have 2 elements that compete for their oxidation, for instance, oxygen and sulfur, it's the big one. Both oxygen and sulfur in their bonded form would like to be -2. But in an element like, or an ion like sulfate, oxygen and sulfur both can't be -2. So sulfate is SO4, 2-. They both can't be -2. So when you have this situation, the element that is most electronegative gets to choose to be the oxidation at once. In other words, I don't know how to explain it better. You never use the word once or likes or anything in your explanations, but oxidation of oxygen, because it is most electronegative, stays -2. That forces the sulfur to be +6, and the entire ion is -2. Cool. Now, when you have 2 elements of varying activity, they're going to exchange electrons until the more active element becomes an ion and the less active element becomes a solid. And that's the basis for electrochem. We can go off through oxidation rules. Are we comfortable with these oxidation rules? +1, -1. Sorry, +1, +2, +3, ±4, -3, -1, -2, -1, 0. Until they have to rearrange. And the D block ones are the ones we care about. That's what we actually have to figure out what they are. So we're comfortable in determining oxidation states by this point? Okay, let's get to electrochem. Okay, here we are. So consider this reaction. This is thermite. Take aluminum powder, iron powder, put them together. They release a lot of heat. Aluminum starts at 0. Ends at +3. Iron starts at +3, ends at 0. So we can make some statements about which of these 2 metals is more active. Because this is a reaction that once it goes, it really goes. It is highly thermodynamically favored. Now, as far as entropy goes, if you balance this, you have 3 solids on the left and 3 solids on the right. You can see, like, you put a 2 here and a 2 here. Okay. So three solids, you have basically a neutral entropy change. But the enthalpy change is massive. It releases a tremendous amount of energy. So it has a very negative delta H. Can you see that in your head? Delta H minus C delta S. So you have a very negative delta H or very negative delta G. This is a highly thermodynamically favored system, which means you have a system where you have a metal that is currently an element that is thermodynamically favored to be, is more active to be an ion. And you have an ion that is more thermodynamically favored as an element. So they will exchange their electrons. From aluminum being 0, it's going to give up some electrons, so it can become +3. The iron being +3 is going to accept those electrons, so it can be 0. So we say aluminum, because it gave up its electrons, is oxidized. And iron, because it accepted those electrons, is reduced. This is nothing new so far, but I want you to, if you didn't pick it up before, hopefully you're picking it up now. That is going to be the theme of April. I didn't understand it. That's okay. I'm not going to be angry if you didn't understand it before, as long as you're going to be fine in 3 weeks. 3 weeks from Monday, by the way. So we call this an oxidation half reaction. We call it a half reaction because it's not balanced. You're like, you're just chucking electrons. Where do the electrons go? I don't know. This is a reduction half reaction. I needed electrons. Where'd they come from? I don't know. You put them together, you get a full reaction. But this is called an oxidation half reaction. This is called a reduction half reaction. Okay? 3 mnemonics. First mnemonic is oil rig. And all of these are valuable to what we're doing. So oil rig. That's what you see if you go to Great Bakersfield in the Walmart parking lot. I'm not making that up. And it is, you can write it down. Oxidation is loss, reduction is gain. Oxidation is loss, reduction is gain. So when you go to Bakersfield or Fresno and you're in the Walmart parking lot and you see the oil rig, just think about oxidation is loss. I was shocked. I almost got a job there. Dodged a bullet on that. My wife is funny. She talks about it when I went to Kern County to interview for the science position there. She's like, "Wow, dodged a bullet there." Okay. So far so good. The next one is Leo says grr. Leo says grr. Loss of electrons is oxidation, gain of electrons is reduction. So, I have one more mnemonic which I'll share with you when we actually talk about the physical devices that harvest electrical energy or produce electrical energy. We talk about our cell phones. We talk about batteries, electrolytic cells, and voltaic cells, and galvanic cells. I'll give you another one. But there you go. So, loss of electrons, oxidation. Gain of electrons, reduction. Can you have oxidation without reduction? No. It takes somewhere. Exactly. The electrons have to go somewhere. You can't just release electrons into space. Okay. And you can't have reduction without oxidation because electrons have to come from somewhere. So you got to have one or the other. And super important, the electrons must balance. Now here it's easy because you go from 0 to +3 to 0, but that is rarely the case. It is rarely the case that the electrons perfectly balance. The AP likes to use +1 and -2s to see if you realize that you have to double the other one. So the electrons balance. That's their favorite. I've never seen them do a 2-3, but they can totally do that for you. I have seen a 1-3, +1 -3. I've never seen a +2 -3 or a +3 -2. But it's fair game. They can totally do it. All right, so moving on. More redox terms. So when you hear things, and this pops up in multiple choice questions, when you hear gains oxidation number, that's just oxidized. Loses oxidation number, that's just reduced. Now, are you comfortable enough that we can skip this in determining oxidation numbers? So zinc here is 0. Copper here is +2. Okay. Nitrate's -1, so silver must be +1. And if nitrate's -1, nitrogen must be +3. Nitrogen is less electronegative than oxygen. Oxygen's more electronegative. So oxygen gets to be -2, -2. Nitrogen has to be +5. Zoom. Let's get to the AP level. All right, here we go. AP level. I mentioned yesterday that a voltaic cell is one that produces voltage. It's got another name because there was this dude that had, you're like, we've got to name after someone. So voltaic cells are named after Alessandro Volta, but they're also called galvanic cells. I wish they weren't, but they are. So I don't know why we have two names for the same thing, but a voltaic cell and a galvanic cell are exactly the same thing. In a voltaic cell, it is a spontaneous reaction where the less active metal becomes a metal and a more active metal becomes an ion. So this is what's going on in your phone right now. The lithium metal is converting to a lithium ion. Because lithium is a highly active metal, it is not thermodynamically favored as a solid. You understand what I mean by solid? Like solid with a 0 oxidation. So there's lithium in your pocket right now that is lithium solid, but it would much rather be a lithium ion. So it is ejecting electrons to make that happen. The lithium solid is ejecting electrons to become lithium ion. Then we are harvesting those electrons to keep a computer working in your pocket. That is a voltaic cell. In a voltaic cell, red cat. I told you there's going to be another one. Red cat. This isn't really, not really a letter mnemonic. It's just something to remember. Reduction happens at the cathode. I don't have one for the anode, but if you have one, please let me know. Red cat, reduction happens at the cathode. Particularly in our computers. So let's look at these diagrams. In this extremely simple diagram, and that's what the AP is going to use. They're going to use extremely simple diagrams for electrolyte. You have an anode here. You have a cathode here. Cathodes are labeled positive. I should stop and just let you figure this out. Why are cathodes labeled positive? In your battery, there's a positive terminal and a negative. There's a positive end and a negative end. In every piece of electronics, like my sensors, there's a red end and a black end. The red end is always the cathode, red cat. Why are they labeled positive?
So that's where the reduction is, and that's where they're giving out the electrons.
First part's right. That's where the reduction is, and that's where the electrons are going. Okay, so they thought, hey, chemistry students might want to tie the general ideas of electrostatics together, that we have a positive thing and electrons move towards a positive thing. So that's what they do. They're like, okay, we're going to make the cathode positive. This happened 150 years ago. we're going to make the cathode positive, so students remember that electrons move towards the positive because electrons are negative. Get the idea? And we're going to label the anode negative because students are going to remember that things move away when they're similar charged. So if you have a negative thing, an electron's going to get moved away from the negative thing because like charges repel. Okay? So you have an anode that is labeled negative. Electrons leave the anode, flow through whatever we want, might be a wire, might be a cell phone, to the cathode. Now, this has to happen in an electrolyte. Last year you learned an electrolyte is a substance that conducts electricity. It's a solution. We'll talk about solutions next time. I don't think we're going to get to it next time, but we'll talk about it eventually. Again, I will adjust the schedule as needed. We have plenty of time. We are right on schedule. So far, 2.5 weeks of review, so we're in good shape. So here you have a solution, and here you have a solution. If electrons are moving from left to right, you are building up a negative charge over here. Nature says no. So to keep that from happening, electrons or negatively charged things must flow through what's called the porous barrier or the salt bridge. One of the most annoying things in chemistry, electrochemistry, is we don't have good actual models of porous barriers and salt bridges for you to play with. I've been looking. They're not even that expensive. It's just they tend to not work properly. But this is a model that you'll actually see. This is actually from an AP textbook. A salt bridge is a glass tube full of gel through which ions may move. A porous barrier is, I'm not exaggerating, a bowl that water can't move through, but ions can. I know it's weird. The ions can actually go from molecule, like porcelain, like a porcelain bowl. The ions can go from molecule of porcelain to molecule of porcelain to molecule of porcelain, but water can't go through them. Kind of like how you learned in biology about osmosis and osmotic filters, where water can go through but nothing else can go through. It's the opposite. Water can't go through, but ions can. The important takeaway is that charge must be conserved. So if electrons are leaving here, a positive charge would build up here, so we have to balance that by moving anions across. Basically, if there's a positive building up, we're going to have to move negatives over to cancel it out. Or in other words, if electrons are moving from left to right, negative ions must move from right to left. Now, depending on what's going on, it's entirely possible that only negative ions are moving. Or it's possible that both positives and negatives are moving. Whatever is required to balance the charges. But the important thing is charges must balance. So what does that mean? All right, let's go back to this. So once you got the general idea, then we can graduate to this. Are you comfortable with this idea of electron flow? Okay, now let's actually add some real metals. Zinc is more active than copper. So the zinc copper cell is the one that's almost always tested. So if you have a zinc cell here and a copper cell here, and you put them into zinc nitrate and copper nitrate, I have a weird question for you. What's going to happen to the mass of the zinc cell? So let's say we hung a very precise spring scale from this electrode and a very precise spring scale from this electrode. What is going to happen to the zinc electrode? Why would it get heavier?
Because the positive ions are accounting for the loss of electrons.
Okay. I told you that zinc is more active than copper. Does a more active thing want to be an ion or a solid? An ion. So a more active thing would rather dissolve into ions. So what's going to happen to the zinc electrode? It's going to get dissolved. Yeah, it's going to get lighter. It's going to dissolve. And this is what happens all the time. Remember gas stations where you put gas in your car? Well, underground at gas stations, there's these gigantic tanks, and they're made out of steel. Problem with that is they're in the ground. You know what's under the ground? Minerals. You know what's also under the ground? Water. You know what happens when steel encounters water and minerals? It rusts. To keep that from happening, we coat the steel with zinc. And we have this giant block of zinc, which is connected by a wire, no joke, to the tank. So instead of the iron decaying, the zinc decays. It's called a sacrificial anode. Zinc is very, very active. If given the chance, it would rather be ions. So what happens is the zinc dissolves into ions, becoming smaller. At the exact same time, the copper, which is less active, does what? It gets bigger, exactly. It swells up, and we can actually see that. Again, one of these days I'm going to have one set up and we can actually see it. I've done it on accident. I've had electrodes just disappear on me because I left them alone, and you will too eventually. But as the zinc gains electrons, the zinc atoms become ions, and the zinc electrode dissolves. At the same time, the copper ions in solution become copper metal, and the copper electrode swells up. And that will keep happening. Okay. Now we've graduated to this diagram. So everything is happening. This is, by the way, a voltaic cell. We know it's a voltaic cell because there's a voltmeter that's measuring how much voltage is created. Everything that's happening. We connect the electrodes together. The zinc electrode, which is more active, becomes zinc 2+ ions. The copper electrode, which is less active, takes the copper 2+ ions that are in solution and turns it into copper metal. This is a solution of zinc nitrate. This is a solution of copper nitrate. Are you with me so far? Okay. If electrons are moving this way, positive ions can move the same direction to balance out the charge. Or negative ions can move backwards to balance out the charge. In the case of this, both is happening at different ratios. But here's the great thing. If electrons are moving this way, and copper ions are sticking to the electrode, becoming copper metal, and at the same time, zinc metal is becoming zinc ions, what is happening to the concentration of the zinc nitrate in this cell? As the reaction proceeds, zinc metal is becoming zinc 2+ ions. Copper ions are becoming copper metal. Electrons are traveling through our wire, through our voltmeter. Nitrate ions, to balance out the charge, are moving from this cell up into this cell. What's happening to the concentration of zinc nitrate in the zinc cell?
It's going up.
It's going up. And that is measurable. We can observe that. The concentration here is going up because as the reaction proceeds, the zinc concentration is going up because it's coming from the electrode. The nitrate concentration is going up because it's going into the other cell to balance out the reaction. At that exact same moment, at the exact same proportions, what's happening to the copper nitrate? It's going down because the copper in the solution is becoming copper metal, which has no concentration. and the nitrate in solution is moving to the other cell. So as the reactions proceed, the electrolyte concentrations change, just as the electrodes change. This is super important, because eventually, we're going to learn with math in a little bit, not today, but soon. Eventually, the concentration here will be too high, the concentration here will be too low, and you won't be able to make enough voltage. And if you won't be able to make enough voltage, then Sophia's cell phone will stop working. And that's what we call a dead battery. This was a big deal for me in the 80s, because I had a Game Boy. You probably don't know. Do you know what a Game Boy was? It had a green and white screen. They called it black and white, but it was green. And didn't have a light or anything. We actually had to hold it in the sun or something. Anyway, it took 4 AA batteries. Those 4 AA batteries, when you took them out of the case, produced 1.6 volts. By the way, most cylindrical batteries are 1.5 volts. FYI. A 9 volt is 6 of those, 6 1.5 volt batteries. Right now you're doing the math. Yeah, it's that easy. But they don't ship them at 1.5 volts, because if they did, they wouldn't last very long. And you'd be like, man, energizers suck. This doesn't last long at all. So they ship them at 1.6 volts. If they ship them at 2 volts, your device could blow up. So they ship them just above where they need to be. Alexa, stop. Well, the problem is, in order for the Game Boy to function, because it was such an extraordinarily complex piece of electronics for the 80s, it needed 5.6 volts. Which means, if you put 4 1.5 volt batteries in it, it'll work until those 1.5 volt batteries are only putting out 1.4 volts. Then they would stop working. So you said, man, this Game Boy eats batteries. But then you could do with those 1.5 volt batteries? Put them in a flashlight. It worked just fine for days. Because as the reaction proceeded, the 1.6 volt battery became a 1.5 volt battery, then became a 1.4 volt battery, and then your Game Boy wouldn't use the batteries because there wasn't enough juice. But those exact same batteries that we said were dead, you could put in a flashlight and they work just fine. The idea? So next time, I'm going to show you the math that is involved here. All right, questions? Call it a day? Call it a day.